That is the optimum solution. So it's about 1.8 something, and then up 2.492 right there. 1.80, 2.492. That is the point that is closest to the point 3,1 on that parabola.
We can do that for any point as long as it's...
You could have done that for any point. 3,1, you could have come out here, 6,2, you could have...
On the other side of the graph?
Pardon?
Even on the
Oh yeah, you could do it on the other side. Absolutely. Yep. Some of them wouldn't be very interesting to do. Like if you put something on the x-axis, right? Then like if you moved it like right here, it would just be straight across. But I mean, you would see that. You would do the calculus and that's what it would produce. I think a more interesting question would be, and this is not something that I would give you, all right, would be like, what if you had another parabola over here like this? To find the pair of points that are closest to one another, right? That would be a more interesting problem. Because this x and y would have some sort of constraint, right? Because they have to live on that parabola. This would live on some sort of constraint, or live on this parabola, so it has some sort of constraint. But the distance formula is still the same, with the exception. God, can we do this? No? No, here, I'll no. No and no. I'm so curious. No, I want to see. Come on, just let me try something. No. But we're going to use technology. We're going to use a computer to take the derivative. We're going to use a computer to set it to 0. We'll see how fast we can find it using technology. So look, I'm going to take this parabola, this one, very simple one. Let's do y equals x squared plus 6. And we'll stick with this one, which was y squared equals 4x plus 1. I want to see if I can find the pair of points that are closest to one another. Okay? All right, so watch what I'm going to do. I'm going to pick a point here. I'm going to call that x1, y1. I'm going to pick a point here. I'm going to call that x2, y2. Y'all don't need to write this down. Just see if you can follow how this would work. I know that the distance between those two is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared, right? Okay, now to live here, you must look like this. X squared plus 6. The x coordinate can be whatever, but the y coordinate has to be this. Right? This one, to live here, the x coordinate is y squared plus 1 over 4, and the y coordinate is y. So what I did there is I solved this for x. Solved that for x and then placed it here. The y coordinate is free to be whatever it wants. Yes? Yes. Okay, so now what I do is I plug them in here. So this will be x2, which is y squared plus 1 over 4, right? Minus x1, which is x squared plus y2, which is y, minus this x squared plus 6 squared. Right? You know what? I don't think we're going to be able to do it with Cal 1. There's a problem here, and that's the x here is different than the x here. Like if I say, hey, x is 2, that doesn't mean x is 2 here. This is a different x. Yeah, so this is going to be basically, yeah, we're solving for like 4 different things. Trying to see if there's any way around it, though. I don't think we can get it. No. It's just there's too many variables, too many things that can move. This point can move, right? And so when this is fixed, like the problem we had here, this was fixed, this point could move but it could only move in a certain way, so I could get everything to a function of a single variable. In this problem that I presented, if this point moves a little bit, right, it changes the answer. And if this one moves, it changes the answer. So there's 4 different things at play here. All right, sorry. We can do it with Cal 3. We just can't do it here. All right. How are we doing on time? 30 minutes?
Yeah.
Fastest route.
Run.
Let's just talk about this one, all right? We might take it the whole way. We might just set it up and at least get to the function. All right, so what we have is a person. This is a perfectly circular pond or lake, okay? This is a lake. And what we have is a person that's trying to get from point A over to point C. They have a little canoe, all right? And they can row across this lake at a certain speed. But they can also just walk around the lake. Just walk around the edge, right? Forget going across. So they can, let me give you some information here. They can row at, I'm just going to make this up, okay, 20 feet per second. That seems fast. That's too fast. Let's go 10 feet per second, which is still pretty fast, but let's just go with that, all right? They can row 10 feet per second. And they can run at 14 feet per second. Because they have to, I mean, that's their, they can maintain 14 feet per second the whole time, all right? That's pretty fast too. The lake, across the diameter of the lake, it's a pond. Let's make it a pond. Diameter is 500 feet. Excuse me. I'm not sick. I just have this cough that won't go away. It's your fault.
No, it is not. It was remnants from last semester just dangling in the air somewhere.
All right. Find fastest and longest route. So here's the idea. This person could just decide to row straight across, right? Just row across straight from point A to point C. They would travel at 10 feet per second over 500 feet. You know how long it would take them, right? But they could also decide to not row at all and walk the whole way, right? Or run. They can run faster than they can row, but they have to go a longer distance, don't they? I shouldn't even joke around. I remember when I was in middle school, one of the English teachers collapsed in class and died. I wasn't in that class, but I just remember that. Okay, so we could row the whole way, we could run the whole way, or maybe we could do some combination of them by rowing to a point over here and then running the rest of the way.
That's kind of like the take-home.
This is like the take-home. The difference is the actual formula. Okay? So when we say find the fastest and longest route, what we mean is time. Okay, I'm talking about in terms of time. The longest route, longest distance, is to go around like that, right? That's the longest distance route. But longest time or fastest and longest routes mean in terms of time, yes? Okay, so let's try and get a grasp on this. What we want to do here, our goal, is to optimize the time function. In your take-home test, you're optimizing the cost function, aren't you? But here we're going to do, and I put optimize because normally I would put minimize or maximize, but in this one I want both. I want both the maximum time and the minimum, right? So let's try and come up with a time function, t. This is the hardest part of the whole problem, is the actual function. Well, let's break it down. Isn't this going to be just the time it takes to row plus the time it takes to run? Whatever those are, right? I may not run at all, so there'll be maybe 0 for time running, and I may not row at all, so there may be no time here, right? Hold on, I'm going to do something real quick. I have the ability here to never mind, just hang tight. Uh-oh. Good. All right. So how about the time it takes to row? That's from A to B, right? Notice how I've broken up this path, right? I've said, look, I'm gonna go from point A and I'm gonna aim to a point B on the other side of the lake. That point B might turn out to be C, but it might also turn out to be kind of A. It's almost like straight up, right? But it might be over here. So if you look at that, it creates an angle, doesn't it? So that angle is either going to be 0 or potentially, what would that be? 90 degrees, right? If I say, hey, aim to a point B. If I say, okay, aim at 0 degrees, I'm going to go straight across. If I say aim at point B 90 degrees, that means I'm going to go up like this and walk around. Understand? Whoa. There we go. Whatever you do, the distance from A to B is how much time you're going to spend rowing. Yes? So what is that distance?
We got to measure it and set it to a time that identifies 10 feet per second.
Is it a trig function? Maybe. So we have something here. This is, I'm showing you this. The take-home's not, the little take-home one I gave you is not like this because it's not on a circle. It's much better trig functions, much easier trig functions to work with. This one, I show this problem because this involves some kind of cool trig stuff. Before we do time to row, let's just talk about something. Rate times time equals distance, doesn't it? You know this formula? Rate times time equals distance. If you're traveling 50 miles an hour for 5 hours, you're going to travel, right? You multiply the two. I've even seen, I'm sure you may have seen something like this. I think it's D, hold on, RT. I've seen these like cool little circles. I don't know. Have you all ever seen something like that? That might be wrong, actually. If you want to know rate times time, it's distance. Time is distance over rate. Rate is distance over time. Has anyone ever seen something like this? It's cute, but it's just this equation. I mean, you could solve that for T or R or D. I mean, it's just cute. Yeah. Yeah. Those are cute things, but you could solve for T here by dividing by R. You could solve for R by dividing by T. You get the same equations. All right. So I did this because time is always the distance over your rate, isn't it? Yeah. Distance over rate. So the time it takes to row should be equal to the distance it takes to row over the rate that it is that we row. Does that make sense? The time it takes to row is the distance it takes that we row divided by the rate that we row at. And then the time it takes to run should be the distance that we run divided by the rate that we run. In both cases, we need these distances. So I need to know what the distance is from here to here. What is that distance? It's a function of theta, isn't it? Yes?
Yes.
So this is the distance we row. And then this piece right here is the distance we run. Agreed? Can you tell me either one of these? They both have to be functions of theta. I give you theta, you give me the distance I run or the distance I row. Do you remember this from pre-cal? Slice of pizza. That this right here, we called this S, which was the arc length. And if this was theta, then this was R. The formula was S equals R theta. But theta had to be in radians. Remember that formula? That's what I'm going to use for distance run. Distance run is going to be the radius, right? Which is what? From where to where? Now we have a problem. These aren't the same, are they? Right? This is tricky, right? This is tricky. Now, if I had the center point going out to here, then that little r I could get the formula from, couldn't I? And do we know what that r is?
That's a
250. So a 500-foot pond, so that would be 250, right? This is strange, isn't it?
So you're going to use that for
I'm wondering when I should bring this in. I think I should probably bring this in now. So the whole purpose of this problem is to kind of introduce you to some trig stuff that you may not even be aware of. All right? So let me show you something. I'm going to get a fresh sheet up here. We'll clear that out and we'll come back to it in a second. All right. This is a theorem. Let's say that you have a circle, right? And there's the center. And you have 2 points anywhere on that circle. Doesn't matter where they are. And you connect them right here. That angle, let's call theta. All right? Now, pick any other point on the circle. So I'm going to pick another point on the circle. I'm going to pick one back here. Doesn't matter where it is. Anywhere I could pick it anywhere back here. So I'm going to pick it right there. And I'm going to connect these points back to that one. There's a relationship between that angle I just formed and the one that was there, theta. And you probably don't know what the relationship is because you may have never seen this. This will always be theta over 2. Now, but the professor who showed me this called this the Star Trek theorem because I guess in Star Trek there's a symbol in there that looks like that. I'm not a Star Trek person. I apologize for being completely unaware. So this right here, this is the same picture. And that means that if this is theta, that this is theta over 2. All right? And what's cool about this is this works no matter where I drag this point to. That it'll always be half. It'll always be half of the other angle. You can really see it if you exaggerate it like this. Like what if I take this point and I pick the point above and below and connect those, right? So that's this piece. Then what's this angle theta? 180, right? Now pick any other point and connect them, and you're going to be 90. But that's just one specific example. You could do it like this also. Here, let's go pick that point and pick that point. What's that angle? 90. So if I pick any other point and connect there to there, that'll be 45. It's a cool theorem, all right? I don't expect that you would have known that. This is why I'm showing you this problem, all right? Because it brings out something you may or may not have known. Also, if this angle is theta, then what's this angle? 2 theta, right? That's the way we're going to use it. So let's go back to our picture again. That should help significantly. All right. So let's find the center of this, which is here. And let's connect here and here. Can you tell me what that angle is? 2 theta. That's 2 theta. Why? Because this point was back here, right? And it connected there and there also. So this is always just 2 theta. And you said the radius of this circle was what? 250 feet, right? We understand that that's feet? So going back to the pre-cal formula that said if you had an arc, that if this was r and this was theta, and this was s, that s was r theta, right? Then that means that this piece here, which is the distance that we run, right, is going to be r theta. So 250 times 2 theta, which is 500 theta. The distance we run is 500 theta. Make sense? But what's the distance that we row? That's from here to here. The distance we row. And how are we going to get that? We've got 13 minutes to get it. Do you know this side right here? That's 250, right? Do you know this side right here? That's also a radius, isn't it? That's 250? You have 2 sides of a triangle and you have an angle in it called theta, yes? So I think we can probably get it with some law of something, right? Let me try and draw that triangle over here. We've got here, here, here. This is theta. This is 250. This is 250. I'm interested in this side over here, right? This side, which means I need to know this angle. Law of cosines, the way law of cosines works is you have 2 sides and the angle between them, then you can find out the information about the side across from that angle. Do you know this angle? Yes, you do. What is the distance from here to here? 2 theta? What's distance all the way from here to here? 180, which is 180 minus 2 theta, but let's use radians. Isn't this pi minus 2 theta? Isn't that what that is? It's pi minus 2 theta. So what now?
Well, now we can discover the hypotenuse.
Let's call this side. I'm going to call it. Yeah. Hold on. Let's call. How about a little a from like when we were studying triangles in pre-cal. We have like triangle ABC, angle ABC, right? So we could do it with law of sines or cosines. We know we can do it with law of cosines. Can we do it with law of sines?
No, well, you know the angle.
What are we trying to solve for? Little a?
Little a.
So what I could do is little a over sine of big A, which would be sine of pi minus 2 theta, is equal to any other side over its angle, sine of its angle.
Little c, 250.
We know that's 250 over
Sine of big C.
sine of theta. Hold on, y'all are. Look, this right here is angle B, side little b, right? Angle capital A, side little a. Little c, big C, right? Law of sines says little a over sine capital A equals little b over sine capital B equals little c over sine capital C. So we can use any of those relationships. I'm using the side we're looking for over its sine of its angle is equal to any of the other sides over sine of its angle, right? And this is a relationship, isn't it? I can solve this for sine of A. For little a. So just move that over to this side. So we get little a is equal to 250 sine of theta over pi minus 2 theta. What the hell am I saying? Over sine theta. Is that an equation for A that has just theta in it? Depends on theta, yes. Now, what would law of cosines been? So that'll work, but would the law of cosines have been a better approach? We could have used this formula here, that a squared equals b squared plus c squared minus 2bc cosine of the angle capital A. And we know b and c are constants, right? These are the 250s. So I could go 250 squared plus 250 squared minus 2 times 250 times 250 times cosine of. I like the law of cosines actually better in here than I do like this one. Okay. There's no way I'm going to be able to finish this. But what would we do if we were trying to set this up? Okay? We would have our time function, right? Our time function would be the time it takes to row plus the time it takes to run. The time it takes to row would be this, right? This right here. The distance that we row over the rate. How fast do we row? I erased it a long time ago. It was 10 feet per second. So if I take this and divide it by 10, that's my time it takes to row. So if we divide that by 10, that just becomes 25, right? So I would have 25 sine of pi minus 2 theta over sine of theta plus, now the time it takes to run would be the distance we run, which is 500 theta, divided by the rate we run. 14? So 500 theta over 14. Does 14 go in there? I don't think it goes in evenly. But that would be it, right? This would be our time function as a function of theta. Y'all follow this or no?
Yeah.
I know I'm kind of like pushing at the end, but I want to get to an answer. That time function depends only on theta. And so I could now talk about the restrictions on theta. So what would my restrictions on theta be? Would this be open interval, closed interval?
Closed.
I go 0 to pi over 2, right? 0 to pi over 2. So my theta is restricted between 0 and pi over 2. So I could use closed interval method. Instead, what I'm going to do is I'm going to graph it. And to graph it, I'm actually not going to use Desmos. I'm going to use something else, a more archaic program called WinPlot. And the reason I'm using WinPlot is because it will find the max and mins easily. So I have, it's going to take me a second to type this in, 25 sine, I have to use x, not x, no, pi minus 2x, 2 theta, over sine of just the x. And then plus 500 x over 14. And I want to lock my interval from 0 to pi over 2. And I'm going to graph this pretty thick. And I need to zoom out. Where is it? There it is. Whoa, way up there. Okay. So it looks like I need to adjust this window. My x is going to go from 0 to, I don't know, I'll go to 3, and then go to 70. There we go. Can you all see that? Can you all see that? That's my time function. It's hard to tell, but it's looking like, to do the shortest time, it's looking like I should let theta be 0. Because that looks like I'm going to get 50, right?
That should be the lowest point.
That should be it looks like the lowest point. Doesn't it look like the lowest point to you? Now, we could plug 0 in and see what we get, but let's now have this find the, looks like the longest time. Let's see, mark point. Next extreme, mark point. Next extreme, mark point. Oh, there it is. Okay. So I had this mark the points for us. Too many windows up there. So you can see the x-axis there. So it looks like at pi over 2, which is 1.57, it looks like 56, it would take us 56 seconds if we do pi over 2, which means running the whole way. All right? So we run around the circle, it's going to take us 56 seconds. If we row to an angle of 0.795 radians, can you hit that? Do 0.795 times 180 divided by pi.
45.
45? Interesting. So if we aim 45 degrees, this is just coincidental. If we aim 45 degrees, row across, and run the rest of the way, that'll be our longest, most scenic journey. It would take us 63 seconds to do that. Okay? And then if we just 0 would be going straight across, right? 0. It would take us, it looks like 50, but it doesn't say 50 here, so I don't. It says 0. That doesn't make any sense. It did. I just marked that point up there. It wasn't the extreme. So anyway, okay, we are out of time. What to do next time? Anything? The problem with the fiber optic, very expensive project.
Can we print it out?
Next time. And then we're going to move on to the next topic, antiderivatives. Time to start talking about the reverse operation of everything. All right, let me shut my camera off. I don't mind taking a look.
I heard that the library.